Hi, welcome to Problem Solving Experts. When something that should happen is not happening, or when something that shouldn't happen is happening, we are having a problem. So what we have seen at this point is that the first thing to do is to define a good problem statement: object, defect, extent, and impact. As soon as you have defined your practical problem, we have to define metrics. We have established technical metrics and business metrics. The technical metrics can be primary ones, the ones that we want to improve, and secondary or counter ones, which are the ones that we don't want to affect. Then we have established the scope of investigation. We have to define two scopes: the scope of the project and the scope of the investigation. And well, basically we have to define where the problem is happening more frequently, when it's happening more frequently, and to whom it's happening more frequently. The next step is to define a project team. We are defining a core team, few people, no more than 8, and an extended team. Then we have defined if we need to do an acceptance strategy. We have done a communication strategy, and then if we have someone with high influence and low support, then we have to do an acceptance strategy. We have to identify the reasons of why the person is not supporting, and depending on that, we have to create the need or do a communication strategy, leadership strategy, management support, or training strategy. And eventually we have to do a change profile in order to reinforce the acceptance strategies if necessary. If with that you have solved the problem, that's it, we are done. We have to implement controls to maintain improved state. But if we have not defined the problem, or where we have not solved the problem, then we have to move from the practical problem into a statistical problem. Then we have to collect data. We have to collect data for the technical primary metric. Well, we have to take a representative sample, and well, we are having a population, size n, and that population is going to have some characteristics. Let me say a mean on an average and a variability on a standard deviation. Basically, what we have to do is to take a representative sample. We have to take a representative sample. This sample, well, things that you have to take in consideration when taking a sample to make sure that you are having a representative sample. Number one, the sample should be taken from the population of interest. Number two, the size of the sample has to be big enough to become representative. Third one, the period of time that we are collecting data has to be big enough to collect all the variations that can happen in the population or for the population. And finally, as much as be possible, we would prefer to take a random data or randomly take the sample. From there, we are going to do some statistics. We are going to define the size, and then we are going to define some descriptive statistics. What is the mean? What is the standard deviation? And from there, we are going to define what is the histogram, for instance, of that population. Once that we have done that, we are going to do inferences. Sorry about that. We are going to do inferences about the population, and these inferences will be inferences from the sample, inferences about the population, and then we are going to describe what are the expected characteristics of the population. So we are going to do inferential statistics. We are going to do inferences, take a sample, and make inferences about the population from this representative sample that we are taking. Well, once that you have collected the sample, by the way, if you have collected the sample by yourself, that is great. But if you cannot collect the data by yourself, because this is a 24 hours collecting of data, 1 hour during 24 hours, or even 3 days, 1 week, etc. So you cannot be there all day long, all week long collecting data, and you have to rely on someone else to collect the data. It is highly recommended that you do a data collection plan. Well, you have your data, but now you don't have to trust that you are having a representative sample. What we have to do is to validate that you are having a representative sample. And that's what I would like to talk about right now, how to validate that our sample is representative. So let's do that. Before analyzing your data, you have to confirm that you are having a representative sample. So there are 4 things that you have to validate to make sure that you have a representative data, a representative sample. Number 1, no outliers or special causes of variation. Number 2, the period of time should be big enough to make sure that you are collecting all the variations that are happening in the process. Good resolution. So the sensitivity of the measurement has to be good enough to capture the variations, sensitive to be able to measure the variability. And big enough. Sample size should be big enough or should be good. Well, let's talk about the first one. The first one is about no outliers or special causes of variation. So sometimes we are having data, we are having a process that is having a variability, but eventually we may have values that are far away from the rest of the others. These values that are far away from the rest of the others, those are known as outliers. Those outliers happen because of special causes of variation. Something special is happening. So the variability that we are observing is not because of the natural variation of the process, but because there is a special cause that is happening, that is making that value to happen. And we say that those values are coming from a different population, not the same population that we have collected or that we want to analyze. Well, what we have to do when we are having outliers is this one. First, we have to identify if we are having a potential outlier. So, well, we have to first identify which are the whisker limits. So usually we can use a box plot, a box-whisker plot. This box-whisker plot is made by, well, quartile 3, which is this one, median, which is the quartile 2, and quartile 1, which is this one. Usually, well, this is going to have also some lines in there which they will determine which are the whisker limit. So this value will be known as upper whisker limit, and this value, which is the lower whisker limit. So that is the expected natural variation of the process. But if for any reason you are having a value, for instance here, far away from this upper whisker limit, or outside, below the lower whisker limit, well, those are potential outliers. What's what you have to do in order to, well, if you are having a potential outlier? As you will see in the diagram, the first thing to do is to investigate if we are having, well, if that value is true, if that is a real value or not. If you identify that that value is not real, then what you have to do is identify, well, try to find what is the real value. If you know the real value, substitute, change the value for the real value. If you don't know the value, what you have to do is just discard, eliminate from the data, and forget it, as if it never had happened. Now, this value is real. This is true. Oh, if this value is real, well, use your descriptive statistics, your mean, your standard deviation, etc., from the data, including the outlier. And now you have to identify if there is a special cause that you can assign. If there is a special cause that you can assign, then that becomes an outlier. Before it was a potential outlier, but as soon as you assign something that can explain that value, then that becomes a real outlier. Well, that's an outlier and you know the cause. What's what you have to do? At this point, you can remove your value, calculate your natural PPMs, your natural sigma, your descriptive statistics, do your inferential statistics, and when you have your final, well, your PPMs, those have to be adjusted because this value was real, so you don't have to ignore the outlier. But what you have to do is to adjust your PPM and making an adjustment to the PPMs to get the real PPMs and the real sigma, including the outliers that were real. Now, if you don't find a special cause, then, well, leave it there. Maybe it's because the distribution is not normal, or maybe it's part of the normal distribution, but still is some potential values can happen. And leave them there and calculate your PPM, your sigma with the value in there. Well, basically that's it in terms of the first test, which is checking outliers. Now let's talk about the second test. Well, the second thing that we have to check if we are, in order to know if we are having a representative sample, is if the period of time is big enough to capture all the variations that we are having. But be careful about that, because sometimes we may think that we are having a representative sample because the period of time is too long. And not necessarily that means that we are having a representative sample, because perhaps our data is data of the last 3 years. But, well, the process 3 years ago is totally different than the process that we are having right now. Then that process that we had 3 years ago is not representative of the current process. I mean, the data of 3 years ago is not representative of the current process. So what we have to confirm, what we have to check is, well, take a look to the data and observe the patterns that we are having in the data. For instance, if we are having something like this one, we are having a lot of data, a long period of time, and then we are having a big change in there, and let's say that last year we had a change in the process because we changed the controller or something. Well, this data is not representative of the current process, is not representative of the current state. So the period of time is big but not representative. Or for instance, also it can be things like this one. We are having a process here, now we are implementing a new control, and once that we implement the new control, well, we have a change here. Something did happen here, and this data is not representative of the current situation, what is happening currently. Also, what it can happen is the other way, that the period of time maybe is not big enough. So perhaps we are having something like here, and now we are having something like here. But we have taken data of two shifts, and we are having the performance of the first shift, performance of the second shift. But the period of time is not big enough to observe all the variations that are happening in the process, because if we were collecting data for shift number 3 and again shift 1 and again shift 2 and again shift 3, we will see that we are not catching all the variations that are happening in the process. So this first period of time is not catching all the variations that are happening in the process, so we have to take a longer period of time. Then what's what we have to do? Well, as I have said, take a look to the data and observe the change of patterns, but try to understand what's behind the changes that we are observing there. By the way, we are having a statistical test, which is Durbin-Watson test, and Durbin-Watson, which is a hypothesis testing, which is checking if there are some change of patterns. If we see a trend, something like is going up or something that is going down, a change of level or things like that, Durbin-Watson will be identifying that something is happening in the process, that we are having something that is changing over time, because Durbin-Watson is evaluating the variation value to value, data to data, one-to-one point. And if we have a change, a consistent change going down, going up, etc., then Durbin-Watson will detect that. So I recommend basically that first you take a look to Durbin-Watson test, take a look to the And the value should be greater than 1 and should be smaller than 3. If you see a value, of course there are tables that we can use, but this is just a general rule of thumb. If your Durbin-Watson value is bigger than 3 or smaller than 1, then that means that there is a change in the pattern of the data. Once that you have observed that your Durbin-Watson fails, the next thing to do, if it's okay between 1 and 3, great, you can move on. But if Durbin-Watson fails, that means that there is a change in the pattern. What we have to do is, take a look to the data. And it can mean that we need to take more data to have because we have seen a change and this period of time is not catching all the variations, so we need to collect more data. Or also it can mean that we are seeing a change and this data is not representative of the current state of the current variation that is happening in the process. Then once that you have done your Durbin-Watson, if it's okay between 1 and 3, great. But if it fails, I recommend you to take a look to time series plot. Time series plot. Let me just make sure this is time series plot. And time series plot is nothing else but a graph over time, and you observe the values on the y-axis here, and time is on the x-axis. And that's it. Take a look to your data over time. It's very important that you don't have to sort your data, but they have to be ordered in a chronological order. They have to be in a chronological order. Take a look to your data and try to understand what did happen in the process or why those changes are happening. And once that you understand that, you will be able to make a decision and know if you have to discard some data, to remove some data, or to add more data, collect more data in order to have a period of time that be representative and catches of the current state and catches all the variations that are happening in the process. Basically that's it about the second test. Let's talk about the third test, resolution. If you observe things like this one, you are having a time series plot, for instance, and you observe things like this one. For instance, that means that, your resolution is not good enough. Why do I mean with resolution is not good enough? For instance, your value here is 7, 7, 6, 7, 7, 8, 7, 7, 6, 6, etc. Assuming that here in your axis you are having 7, 6, 7, or 8, those are the values that you are observing. What do I mean that resolution is not good? Your measurement is not catching the variations that are happening in the process. Every process is having variation. Everything is having variability. Variability cannot be eliminated, only can be reduced. And that's a continuous improvement process. We continuously will be looking for ways to reduce and reduce and reduce variability, but never will be able to eliminate totally the variability. The variability always will happen. Because one of the main objectives that we should have when improving something, when improving anything, is to reduce variability, to reduce the standard deviation, to reduce the spread of the data. The first thing is that we should be able to measure the spread, should be able to measure the variability. So our measurement has to have the sensitivity to be able to catch the variations. But if we are having things like this one, 7, 7, 7, 7, that means that our measurement is not catching variability. Our measurements are not is not sensitive enough to catch the variabilities, and we are observing exactly the same data. So when you take a look to your time series plot, because keep in mind that this data is over time, we are having time here. When you are having time over time and you see flat shark teeth, flat, shark teeth, something like that one, that means that we are not having good resolution. Well, how to know if our resolution is good or not? Well, one way is that with perception, just taking a look to the data and observe the data to see if you are observing variability, you are not observing flats or shark teeth. Now, another way is to do a histogram with double number of natural bars. And what do I mean with that? A histogram, well, a histogram is made by this one. Basically, a histogram is a graphical representation of the distribution of the data of the sample. So, for instance, we are having a sample that is having a histogram like this one. So we are having a graphical representation. Here we are having the values, and we are having the frequency. Well, how many bars should have our histogram? The number of bars of our histogram, there are different ways. One is using the log 10, 3.33 log 10 of the number of values, but which is the one that Minitab is using. But usually what I would prefer to use is a square root of number of values. So we are having, for instance, 25 values. The number of bars for 25 values will be 5. And we would have a histogram like this one with 5 bars because, well, that's basically a natural histogram with a natural number of bars. To check resolution, recommendation is to do a histogram with double number of natural bars. So, if we should have a histogram, if the size of the sample is 25 and we should have 5 bars, then my recommendation is that you do a histogram with the double number of the natural bars. In this case, we should do a histogram with 10 bars and observe to the histogram. And well, we can have two things. We can observe two things. The two things that can happen when you are doing a histogram with the double number of natural bars are these ones. You can have a histogram like this one, which means that resolution is very good, because even although you are increasing the number of bars, you are having values in the middle between one and another and other number, or on each of the bars. But when your resolution is really bad, you are going to have things like this one. Instead of having a histogram like this one and with 5 bars, maybe your histogram with 5 bars is like this one. But when you do a histogram with 10 bars, the same value, the same data, you can get something like this one. And that means that you are having values of 5, 6, 7, 8, 9 in the example that we are saying here. So you are having values here of, for instance, of 7, of 6, of 8, etc. The example that I'm having here. But we are not having any value in the middle, between 6 and 7, between 7 and 8, between 8 and 9, and etc. So that means that you are going to have many blanks here, many empty spaces. If you are having many blanks or many empty spaces, that means that you are not having a good resolution, because you are not catching all the variations that are happening, well, or you are not catching variation, basically. So the variability that is happening is not being caught. You are basically having repetitive same numbers. Rule of thumb: if your empty spaces, your empty bars, your blanks is smaller than 25%, of empty bars, that means that you are having a very good resolution. But if, for instance, you are having more equal than 40% of empty bars, that means that your resolution is not good. What do you have to do? It's not a matter of collecting more data. It's not a matter of you are not taking a sample that is coming from the population of interest, but it's a matter of sensitivity. What you have to do is to collect data again, or maybe can be the same data, but try to report more digits. For instance, if you're reporting 6, 7, 8, report with one digit, 6.1, 7.3, 8.2, etc. So at least one decimal or one digit. Of course, if you're reporting one digit, report 2 digits, or etc. And in that way, you will be fixing the resolution, so the data that you are collecting is catching the variations or the variability that is happening in the process, and you will be able to have a good measurement of the variability. Well, the last test is related to sample size. Well, basically, maybe that is the most well-known test in terms of a characteristic that a sample should have in order to be representative, which is the sample size. Because usually people challenges, when people are challenging, are you having a representative sample? What they really are thinking about is about the sample size. For the sample size, well, basically maybe the best way to determine the sample size is through this formula. Sample size for estimation. We have to define an error. We have to use the t-test, the t-table. This is coming from t-student table, t-test. And well, basically the standard deviation of a small sample. So we take a small sample and we calculate the standard deviation for that small sample, goes here. This error, well, the error varies. A rule of thumb about what should be the size of the error basically is that the error is equal to 10% of the tolerance. And well, what is the tolerance? That is a rule of thumb. Usually you have to determine what is the error that you are willing to take. So the tolerance can be given by the upper specification limit minus the lower specification limit, or that is if you are having a two-sided specification limits. But if you're having a one-sided specification limit, you are having a lower specification limit, greater is better, or you are having an upper specification limit, smaller is better. The tolerance can be given by 2 times absolute value of the specification limit minus the mean of the sample, the small sample that you have taken. And that's how you determine the error if you don't have an error that you can that you have in your mind that you can accept or you are willing to take when error for the mean in terms of the error between the mean of the sample and the mean the actual mean of the population, for instance. But well, anyway, so we are going to use this formula, and that's a good way to establish the sample size. The problem is that usually when you are having a problem, your baseline performance is bad, and then the standard deviation is big. If this standard deviation is big, the sample size will be big as well. So I recommend to use this method when your initial performance or your the performance that you are measuring, your baseline performance, for instance, is a sigma of 4 or greater. If you are having a medium-sized problem, sigma 4 or bigger, a small problem, then you can use that formula with no problem, because usually that's going to give you a smaller sample size, because the standard deviation will be small relatively to the specification limits, because as I have said, your sigma is 4, 5, 6 sigma, etc. Now, how to avoid to collect a big sample, and maybe that big sample is not necessary to have a representative evaluation of your baseline performance. There is another method that I prefer to use when you are having a sigma smaller than 4. And again, that is only for the purposes of ppm and sigma calculation. Do not use this one for other applications like hypothesis testing, design of experiments, or any other thing, but just basically to determine if you are having a good representative sample when evaluating your baseline performance in terms of ppms and sigma. And that is stability of ppms. What is the stability of ppms test? What is it about? Well, you are taking a sample and then you are having your data, and you will be calculating your ppms, assuming that here you are having more data, before you are having more data, and you are going to calculate the ppms with these values and all the rest. Then the ppms with the first values, the ppms with all these values, the ppms with all those values, and so on. So at the end, you will be calculating ppms every time that you are adding one value to your sample. And take a look to the variability or the variation that you are observing during the last few numbers. For instance, we can see a variation of 5,000 out of 100,000, so that is a variability of about 5%. So this is about 5% of variation. This variability is about 1%. This variability is about 2%. This variability is about 5% again, and so on. This variability is about I don't know, 9%, for instance, and so on. So you will continue checking the variability that you are having from ppm to ppm calculation. So what you want to confirm is if the ppm is stable, the ppm calculation is stable. If you are having big variabilities, big percentages of variation on ppm, that means that your sample still is not representative of the population because you are having a high uncertainty. But if the variability of the ppm calculation is very small in terms of percentage, that means that you are having a representative sample, because it doesn't matter if you are increasing more data to your sample, the ppm calculation remains about the same. So that means that the ppm calculation is close to the actual ppms of your population. Then I recommend that you take a look to the last 5 percentages of variation. So in this example, 1, 2, 3, 4, 5. In the last 5, you shouldn't have anything with a variability greater than 20%. If you are having a variability greater than 20%, that means that you should keep collecting more data. And take a look to the last 3. And in the last 3, you shouldn't have any variability greater than 10%. Again, if you are having more than 10%, that means that you should keep collecting more data. And basically, that's how you are going to establish if you are having a representative sample in terms of size. Let me just summarize. If your initial sigma, your baseline performance, is greater than 4 sigma, use sample size for estimation, which is this formula. But if your size is bigger than your sample, you should increase your sample until you reach this value. If your small sample is equal or smaller than this value, your sample size is big enough. Now, if your initial sigma, your baseline sigma, is smaller than 4, instead of using this formula, I recommend to use the stability of ppm's calculation. Well, when you are having a problem, that means that something that shouldn't happen is happening, or something that should happen is not happening. Then the steps to take are: number 1, define your practical problem statement. Number 2, establish metrics, technical, business metrics. Number 3, determine the scope of project and the scope of investigation. And number 4, establish your project teams. Now, once that you have done that, identify if you are having enough support, if you are having people willing to support to solve the problem. If not, you have to fix that doing an acceptance strategy. Now, sometimes with the acceptance strategy, more involving people, more involvement, more collaboration, then you solve the problem. But if this is not a problem related to willing, related to wanting to do things, then it's something technical, it's something related to that we don't know what is the root cause or we don't know what is the solution. If that is the case, then we have to convert the practical problem into a statistical problem. So the first thing is to establish our baseline performance, determining how big is the problem. If we are having a small sigma, let's say smaller than 2, we are having a very big problem. Between 2 and 3, we are having a big problem. 3 to 4, medium size problem. 4 to 5, small problem. More than 5, a big problem. And then we have to calculate the sigma. We will be calculating ppms or dpmos. As much as be possible, we would prefer to calculate ppms, which is a probability of having defects. To calculate that probability, you have to collect a sample, and that sample has to be representative of the population. So you have to collect your data, and in order to make sure that you are having a representative sample, there are some tests that I recommend you to do. Number one, take a look to Box-Whisker Limits to make sure that you are not having outliers. If you are having an outlier and you know the cause, remove the outlier, calculate ppms, and adjust the ppms. If that is a real value and you don't know the cause, calculate the ppms including that potential outlier, which is not a real confirmed outlier because you don't have a special cause that you can assign to that value. The second test is evaluate Durbin-Watson test. If D is between 1 and 3, that means that there is not an evident pattern, an evident trend, etc. in your data. But if Durbin-Watson is greater than 3, smaller than 1, I recommend you to take a look to time series plot and try to understand what is creating those patterns in your process. It can be because there is a temporary situation that is not representative of the current situation, or it can be because the original data, the first data that you had, is not representative of current situation, or it can be because you need to collect more data in a longer period of time to catch all the variations that are happening. In any case, you have to understand what's going on and determine if you have to remove, shorten, or enlarge the period of time in terms of collecting data. And using, of course, time series plot to analyze the data. To observe and then analyze the data. The third test is good resolution. We want to reduce variability, but we cannot improve what we can control, and we can control what we can measure. So the first thing to do is to make sure that you are able to measure the variability. If you are having data with no good resolution, you are having the same values, that means that your resolution is not good, so you are not able to catch all, your measurement is not sensitive to measure the variabilities, and then you have to change the sensitivity of your measurement in order to catch the variability and having a representative, a resolution, a good resolution. And you can do that doing a histogram with double number of natural bars. If you are having many empty bars, more than 40% certainly of empty bars, certainly that's not a good resolution. If you are having less than 25, you are having a good resolution, so you can move on. And the third one is sample size. Big enough, so you have, in order to have a representative sample, if your sigma is smaller than 4, I recommend that you use a stability of ppms calculation. Last 5, no more than 20% variation of in ppms. Last 3, no more than 10% variation on ppms calculation. And if your initial sigma is 4 or greater than 4, then you can use the formula to calculate the sample size for estimation. And once that you are sure that you are having a representative sample, then you can proceed to calculate your ppm, your sigma, your baseline performance. And that's it for now.